So actually, this is what we call the Gauss Law. And Gauss Law relates to the net flux phi of an electric field through a closed surface, Gaussian, or we can call it a Gaussian surface, to the net charge Q enclosed, that is enclosed by the surface. It tells us that epsilon naught, which is a constant, as you know, which is 8.85 times 10 to minus 12. And this is the net flux for this closed surface, or what we call the Gaussian surface. Which will be equals to Q enclosed. Q enclosed is somehow like what you have learned, the F equals MA, F equals MA. Or in circuit analysis, you should have learned V equals IR, somehow like this. So it's a very beautiful expression. You only have 3 variables. So if you know 2 of them, then you can calculate the other. But this one is not very easy to use. Actually, in high school, you can use F equals MA to calculate something, maybe the constant speed or maybe constant acceleration. But well, now you can actually maybe A should be written in small letter. Yeah. Acceleration A usually written in small letter. So actually, if you know the calculus, you know that A is the derivative of the velocity. So we can write it as dv dt. And you also know that V is the derivative to the position. So we can actually write it as d2x dt squared. So if we write it as F equals m d2x dt squared, it will be we can use it in a better way, so that we can actually solve some more complicated problem. And similarly, in this case, this equation looks very simple, but it's not good to use. Not good to use. So actually, we can just substitute the definition of the phi here, so that it looks like this integration law. So actually, this is the E field, the Gaussian integration for the E field with respect to a closed surface. Yeah, closed surface means there's no hole on it, roughly speaking. So and we only consider the charge which is enclosed by this Gaussian surface. So we can consider four cases. Yeah, there are 4 surfaces: S1, S2, S3, and S4. So let's consider S1 first. S1 is the darker orange one, so which is smaller. It doesn't necessary to be a sphere, or it can be any shape. It can be any shape. But if you need to really calculate something, then it would possibly be better to be a symmetric shape, like spherical, cylindrical, or whatever, or cube. But here's just a demonstration. So suppose S1 is like this, with a very strange shape, but it encloses this positive charge. So we know that all the electric field lines are going outside to the across this S1, which means that phi is larger than 0. phi is larger than 0. And actually, Q is positive, so which will match this condition. Although there is a negative charge here, but it doesn't really influence the net flux across the surface. So for the next case, S2 is this one, also the darker orange one. So it only encloses the negative charge. So similarly, all the electric field line going into this surface, which means that the phi is negative, and the charge is negative. So it's written here, phi 1 is larger than 0, phi 2 is smaller than 0. So the net charge, the net flux across this surface doesn't really related to this positive charge. Okay. So for the next one is S3. S3 is this one. So both the positive charge and the negative charge are outside of this one. So the charge enclosed by this S3 should be 0, right? And you can see that the electric field line here is going into it, and here is going outside it. But the Gauss law tells you that when you add all of them together, some are negative, some are positive. It turns out to be 0. So it tells you that phi 3 is 0.
Why not there? I suppose the middle vertical lines between 2 points, they are there.
Not necessarily all the points are 0. There will be some points are. This one is negative for the points here. For the surface here, the phi will be this part will be negative. This part will be positive. But when you calculate the phi, which means that for the overall surface, so you add out something negative and positive, and then the sum will be 0. Okay, it's somehow like you can add 0 plus 0 plus 0 plus 0 equals 0. You can also have something like 4 plus 3 minus 5 minus 2 to be 0. It's somehow like this. So this part is positive, this part is negative. And the Gauss law tells you that as long as the charge enclosed by this surface is 0, then the net flux across this surface is also 0. So of course it has another constant term. The net flux should be, or you can regard it as phi should be Q enclosed over epsilon naught. Somehow like this. This flux doesn't necessarily. It's not actually the charge, but the charge divided by this constant. So for the fourth case, so S4 is here, is an X shape, the largest one. So it encloses both the positive charge and negative charge. So somehow like positive Q here, negative Q here. So the total charge Q enclosed is plus Q minus Q, or plus negative Q. So which will be 0. We considered all the charge enclosed by the surface S4 for S4. So in this case, the total charge enclosed by S4 is still 0. So it tells you that the net flux over S4 is also 0. although you can see this line is going inside. So negative for this part and positive for that part. You can see the electric field line are going outside. But when you add all of them together, it turns out to be 0. So we can see that there are 4 cases: phi 1 larger than 0, phi 2 smaller than 0, phi 3 and phi 4 are all 0. Although phi 3 enclose no charge, but S4 enclose both the positive and negative charge with the same magnitude. Any questions regarding to this one? This is really important. This is really important. The Gauss law will continue to exist up to like chapter 25. So you'll see Gauss law in the next chapter and the next actually in the next 2 chapters. Maybe later on you still seeing it. Any questions? Okay, so actually I'll tell you that Gauss law is compatible to the Coulomb's law. In chapter 21, we learned the Coulomb's law, which is the law to quantify the electrostatic force between two charged particles. And in chapter 22, we know that we don't really need to consider the electrostatic force. We only need to consider a charged particle. It will generate a field called the electric field, which will influence other charged particles. So it doesn't really matter what the test charge is. So in chapter 22, and according to the Coulomb's law, we know that E is like this for a charged particle. And actually, using the Gauss law, we can actually derive the same expression for a point charge. So as you can see here, this is the charge. This is the Gauss law. So we will have E dot dA here, which means that so actually you see that suppose this is the Gaussian surface. It doesn't really matter how large it is. You only consider which point you consider. So actually, suppose it has a radius of small r. Yes, small r. And we will consider for actually this part actually is a sphere, but I can only draw a circle. So you consider it's a sphere. So here you can imagine the E field at this point should point to this side, or the E view at this point should point to this side, And actually, for all the points on the surface, the dA should also point to the same direction. dA. So actually, we know that when the dA should be perpendicular to the surface itself, but actually for a sphere, it is radial distance, radial direction. It should be the radial direction, 径向. So actually, we know that E dot dA, as long as they have the same direction, which means that we should have dA cosine 0 degree, right? they should have the same direction for all different dA. So actually, we can simply write it as EDA, which means E times dA, and is equals to Q enclosed, which is come from the Coulomb's law, and actually the Q enclosed here is nothing but small q, or maybe we can just make it Q enclosed here if you like to make the equation consistent with the figure. So actually we have the equation like this, and E should be constant. E should be constant. We already we can imagine it's only related to the distance. So for a sphere, the distance from the point charge to every point on the sphere should be the same. So we can imagine the magnitude of E is constant over the whole surface. So E can be factored out as long as E is constant for the integration region. So in this case, is nothing to calculate the surface area of a sphere, which should be 4 pi r squared. I'm not sure whether you have learned it in high school, but actually you may remember it if you have not. And actually, maybe you can derive it using calculus. Yeah, you can derive this one using calculus. I suppose you should be able to calculate the volume if you have a line and then this line is rotating with respect to the x-axis, then you can calculate the volume enclosed by this curvature. So actually, you should know that the surface area, actually that's the volume, but maybe the surface area is another, sorry. Well, actually the surface area is nothing but 4 pi r squared. So we just substitute 4 pi r squared into here. So we have epsilon naught E 4 pi r squared equals to Q enclosed. And then we just divide both sides by epsilon naught 4 pi r squared, so that we can have this beautiful term, the K 1 over 4 pi epsilon naught and Q enclosed r squared, which is a very familiar formula. So this tells you that the Gauss law is totally compatible with the Coulomb's law. Any questions? Okay, so let's see an example problem. So in cross section, a plastic spherical shell. Plastic means it is insulator. So it may be a little bit different for a conductor. So you need to be careful about this term, which is usually a trap in a question. So plastic may be important to you. So a spherical shell, but it's only show a cross section. So, but actually you need to imagine it's a sphere. Otherwise, if it's a whole sphere, you cannot see what is inside. So you cannot see the Q. So it only shows the cross section. So a sphere shell with uniform charge, capital Q equals -16e, and the radius r equals 10 centimeter. A particle with charge small q at the center. So small q and big Q. This is negative plus 5e. This is negative 16e. What is the electric field at the point P1 at radial distance R1 equals 6 centimeters? So this point. Okay, without the Gauss law, it might be very difficult to calculate this one because for the q, for the small q, it will be trivial because you can calculate the point charge at any point. But for this one, other than calculating in a far away distance, it might be very difficult to calculate the E field at this point because you need to integrate this one. This charge will generate E field at this point, and then you need to integrate it. Then this integration might not be very definitely not be easy to calculate. So if you can make use of the Gauss law, you can calculate the E field at point P very easy, in an easy manner. So actually, for point P, it is nothing but you consider a Gaussian surface with radius R1. So this is R1, this is R1. So you imagine there is a Gaussian surface. You have a Gaussian surface here. You have a Gaussian surface here. I don't draw it here, otherwise it may be very messy. So so you can consider a charge here, and then with a Gaussian surface, and the ring is outside. So according to the Gauss law, Q enclosed is nothing but small q. The capital Q is outside from this Gaussian surface. So according to the Gauss law, epsilon naught surface integration of E dot dA is equal to Q enclosed of question A. So so you know that yeah, this one is the E view on this Gaussian surface with respect to this one should be constant. So you can imagine it is epsilon naught the integration of dA equals small q. So it is nothing but epsilon naught E 4 pi R1 square equals to small q. So E should be 4 pi epsilon naught quantity inverse and multiply by Q which is 5E over R1 square. Yeah, R1 square. So we can substitute all the number in it. So we have 8.99 times 10 to 9 times 5 times 10 to 1.6 times 10 to minus 9. Yeah. So over yeah, R1 is 6 centimeter, so 0.06 square. So it is nothing but 2 times 10 to minus 6 Newton per coulomb, or you can write it as 2 mu n over c. So actually, the sphere contribute no electric field at point 1. You can see that because we don't have any capital Q here. But if you really need to consider, or you really need to integrating this E field, it will be very tedious, and then you just turn out to be a 0. So the Gauss law tells you that you don't really need to integrate over this circle. It will be equally 0 at this point because it's all the way outside this Gaussian surface. So for part B, it asks you what is the E field at P1, P2 at P2. So for this case, I don't totally repeat, but it will definitely be 1/4 pi epsilon naught times Q enclosed part B over R. Maybe I should call this one R2, which is this one, R2 squared. So this one should be negative 16e plus 5e, which is minus 16e. So it should be 8.99 times 10 to 9 times minus 11, 1.6 times 10 to minus 19 over 12 centimeter, which is 0.12 meters squared. So you must be very careful about the SI unit because for the SI unit it should be meter for the length, not centimeter. So you need to convert it into meter. But sometimes if you have a ratio between two lengths, which is both centimeter, then they will cancel that, and it's just fine. You don't really need to convert it then. But if it just appear once, the meter here, you should use the meter here rather than centimeter. So the answer is minus 1.1 Newton per Coulomb. Actually, if you draw it out, the x-axis is the R, and the y-axis is the E, the magnitude of E, or actually the magnitude of E. So it should be somehow like this. Here is 5e over 5e k over r squared. So this one is 10 centimeter, and it will be somehow like here, negative 11e k over r squared. It will be somehow like this. Inside it will be 5e, outside it will be 11e. Minus 11e over k over r squared, because when r is smaller than 10 centimeter, when you have a Gauss surface here and then you further increase, then it only encloses this Q. But after r is larger than 10 centimeter, you enclose both of them. So the total charge change from plus 5e to negative 11e. So Any question regarding to this problem or up to now? Okay, so let's see another one. So yeah, yesterday we have another sample problem. We have actually calculate phi left, phi right, phi top to be negative 12 Newton meter square per Coulomb 3616. So it is obvious that phi fronts, this is fronts, that one is back are all zero because E only points to only have x-axis component and y-axis component. It doesn't really have z-axis component here. So E doesn't have any component with the same direction of dA like this or like that dA. So it is obviously these two are all zero. So it asks you that what is the net charge enclosed by the Gaussian cube of sample problem 23.2. So actually we know phi left, phi right, left, right, and top. So we still don't know what is down. What is down? Find down. Well, or find bottom. So find bottom. Find bottom. If you refer to the previous sample problem, you may still remember that we can calculate like this, and then the y component, the y component of the E view is 4j. So E is 4j, E dot 4j. I mean we have 4j here, and dA should point to the negative y-axis, which means it will be negative j hat dA. Negative j hat dA. So we have 4j hat dot negative j hat. Ouch. We have negative j hat dA here. So this one will be negative 4. And integrate b dA. And dA is actually 4, 2 times 2. 2 times 2 for this cube. So it is actually minus 16 Newton meter square per Coulomb. Oops. Coulomb. So the total phi, you can add all of them together. Minus 12, 36, 16, minus 16. So it turns out to be 24. 24 Newton meter square per Coulomb. Okay. So Q enclosed will be nothing but epsilon naught phi, which is 8.85 times 10 to minus 12 times 24. So the answer will be 2.1 times 10 to times 10 to minus 10 Coulomb. Or you can write it as 210 picocoulomb, which is also fine. So actually, when we know the electric flux or the net flux across this cube, we can know the total charge within it. Although we don't really know how the charge is distributed. We actually don't know. We only know that there are totally 2.1 times 10 to minus 10 coulomb charge inside this cube. Okay, so any questions? Okay, so next, a charge isolated conductor. In the previous chapter, I've already told you that this one will appear again. So it's now. But for this case, it's a little bit different. It tells you that an excessive charge is placed on an isolated conductor. So this is a conductor. That amount of charge will move entirely to the surface of the conductor. None of the excessive charge will be found within the body of the conductor, which means that maybe you can consider this one. So it's a cross section. So this is the surface, and this is the metal. So it doesn't really draw that part, and it tells you that the charge, if it is a positive charge, it may be, it is still good if it is a negative charge, but no problem. So the charge, suppose it is a very large, so if I really need to draw, I need to draw for the whole one. So the charge will only appear on the surface. It will not be inside. Because if you use the Gauss law, then you know that there will be some electric field inside. Then if it is some electric field inside, there will be some force acting on it. Then you go away. So in a static state, you will go to the outside. You go to the outside. You go to the surface. So if you draw a Gaussian surface like this one, then there's no charge inside it, and there will be no electric flux across this Gaussian surface, and it will be good condition that no charge will move, and no charge really need to move inside this picture. So actually for conductor, you need to consider all the charge should be on the surface. But for this one, it only consider it may be a very large conductor. So it may extend to far away, and at that side we don't really care. We only consider this side. So we can only see this surface here. We can only see this surface here and the charge on the surface. So now we draw a Gaussian surface, but it is not a sphere. For this case, it is a cylindrical. Actually, it is inside. It's somehow like this. If you see the cross section, then you will see a rectangle. But actually, it's a cylindrical. If you just see it with a small angle, so you can see the circle here. But if you are totally perpendicular to it, you can only see a rectangle. So this is a Gaussian surface we define. So in this case, we still use the Gauss law, and actually the integration can be simplified to this case. Actually, it's still Q enclosed. Q enclosed is nothing but this part. Q enclosed is nothing but this part. This part is Q enclosed. And you can imagine, in the previous chapter, we know that all the E field lines should be perpendicular to this surface. Perpendicular to this surface. So the electric force across this side and this side should be zero. And we also know that there will be no electric field inside the conductor, so that the electric force across this side is also zero. So the only side which will contribute the electric force is actually this one. It's only this one. Only this side will contribute the net flux. And actually, this is a circle. This is a circle. So, it should have an area. It should have an area A. So it is nothing but EA. So because the E field is perpendicular to the surface, and this side is the vector dA also perpendicular to the surface. So E and A should have the same direction. E and A should have the same direction. So E dot dA is nothing but E times A, and then it's a constant. So the integration turns out to be just a multiplication between the E and A, which is the area. And we know that, we also assume that the charge density, the surface charge density on this surface is similar to the previous case we talked about yesterday. So we have a charge density sigma. So Q enclosed should be sigma times the area. And in this case, A and A can be cancelled. A and A can be cancelled. So we divide epsilon naught on both sides. So it turns out E to be sigma over epsilon naught. Sigma over epsilon naught. So you may have question in the last chapter. In the last chapter, we divide E to be sigma over 2 epsilon naught. 2 epsilon naught. Where's these two goes? Are they conflict with each other? The answer is no. The answer is no. For this case, we consider a conductor which has a thickness. So the charge here only generate the E field on this side. We don't really care about what is happening at that part. So here we have epsilon naught sigma over epsilon naught. So we have E to be sigma over epsilon naught. And for this case, we have a disk. If we see it on the side, So it is infinitesimally thin disk. It's a very thin disk. So all the charge are on it. So it will generate an E field on both sides. So on the left side, it is E to B sigma over 2 epsilon naught. On the right side is also, but they don't really actual cancel with each other because the E field on this side and the E field on that side are not interacting. So, but actually, the total energy stored in this E field should be the same. When you add them together, they have the same energy. So this explains why there is a 2 in the formula that we derived in the previous chapter, and here we don't have these 2. So let's see another sample problem before we have a short break. So actually this one, the figure A shows a cross section of a sphere metal. So sphere metal shell of the inner radius r. So this one is r, and the point charge -5 μ c is here, and is located at a distance r over 2 from the center. So r over 2. So it's not actually in the center, at the center of the sphere. So if the cell is electrically neutral, what are the induced charge on its inner and outer surface? Are those charges uniformly distributed? What is the field pattern inside and outside the shell? So this is very interesting. So actually, because this one is conductor, although it is electrically neutral, it will have something interesting, which is called the induced charge. So just now I mentioned that there will be no electric field inside the conductor, as it has some thickness. So if we have a Gaussian surface inside this sphere, so the net flux should be 0 because there are no E field in the conductor. So when you add all the zeros together, it will be 0. So the net flux should be 0. If the net flux is 0, according to the Gauss law, the charge enclosed by this Gaussian surface should also be 0. But we have a charge -5 μ c there. So there should be a positive 5 μ c induced charge at the inner surface. So we will say that plus 5 μ c charge on the inner surface to make the overall charge enclosed by this Gaussian surface to be 0. And actually, for the inner surface, the charge will not be equally distributed. For this side, it will be more dense, and it will be less dense at the other side. It's hard to tell why. And it also tells you that because the sphere itself is electrically neutral, so the total charge, which means the total charge is 0. And we have induced charge positive 5 μ c for the inner surface. So there should be -5 μ c charge on the outer surface. So that when you add all the charge together, it will be 0. And in this case, for the outside, we can only see the -5 5 μc charge. You only see the 5 μc charge. You can imagine you draw a Gaussian surface outside, then the total charge inside of this is 0, this is 5 μc. Then we can see the 5 μc. This is quite interesting. So we have a ring. And actually, the center is here, and the negative 5 μc is placed here, negative 5 μc. So if you draw a Gaussian surface with the center, which is the same as this one, then you definitely find the Q enclosed by this one to be negative 5 μc. So when you calculate the E field generated at this point, you can consider this 5 μc goes to here. So it's just like a shield. It's just like a shield. 一个盾牌那样. No matter, even though this charge is not at the center, but after the shield, it feel like the charge is at the center. If you just sense the E field outside. So when you calculate the E field here, you should consider something like the charge is here, because we have a shield here, and the negative charge will be distributed uniformly for the outer surface. It is very